Um, so this talk is going to be on integrated RF converters, and that is kind of a really specific area for ADI. So I'm not going to be talking about like standalone ADCs and DACs. These are integrated solutions, and they're kind of a little confusing to find if you look through our parts lists. And I just want to talk a little bit about some of the historical parts and where this kind of fits in with other solutions that we've had in the past with things like the integrated transceivers. So if you're not familiar with like standard radio architectures, historically there are like three main architectures. Superhead, which has kind of been around forever and been the kind of golden standard over the years, has multiple IF stages that can exist in a radio, where you're using one mixer or multiple mixers in the system, and that's kind of the gold standard in performance. And then in the bottom here is a zero IF type architecture, where you don't have an intermediate frequency. And this is a sometimes called direct conversion transceiver. And if you have a 9361, 9371, or our latest generation transceiver, 9009, this is the architecture that's inside those chips. So they just have a single LO that brings down that RF frequency to baseband. And recently, there's been a lot of work that's been done, development that's been done on the converter side for direct RF chips. And these have no mixers on them, so they directly convert the spectrum. And this has a requirement that they have to be very, very wide, like gigahertz of bandwidth, which really hasn't been possible until the last probably like 5 years. Now, the family of chips that I'm going to be talking about is called the MXFE chips, also known as the mixed signal front end parts. And the Hermes SDR that kind of Ben was talking about yesterday has a 9866 on it, which is a family or part of that family of MXFEs. And this is, I think, the first generation of MXFEs that existed. This is just a block diagram of the actual part itself. So an MXFE has ADC and DAC with some DSP inside it. Usually it's just like some downsamplers or some DDCs or some upconverters or digital upconverters to get you a little bit faster, and maybe some filtering as well. So the 9866 that's inside that Hermes board has single 12-bit ADC, single 12-bit DAC at 80 megasamples a second. And I wouldn't necessarily call this a RF DAC or RF ADC, but if those are your RF frequencies that you're operating at, you might kind of classify it that way. Kind of something similar in that category is the M2K, or the ADLM 2000, which also has a MXFE part inside of it. It has a dual 12-bit ADC and DAC, and these run a little bit higher at 100 megasamples a second and 170. Now, something that just came out recently that's a pre-release part is this, the 9081. So this is a quad or dual ADC that runs at 12 gig for the transceivers, or for the transmitters, and 4 gig for the receivers. So lots and lots of bandwidth. And you can see that the diagram did get quite a bit more complicated in this design. So this part has a lot of other features inside it. So it has like fast frequency hopping, programmable FIRs. The programmable FIR actually has a crossbar, so you can do IQ rotations and things like that inside. And it is JESD, so it's JESD 204C, which at max rate for this part will do 24 gigabits per second over the serial link. Just a little bit of information on the part. So in red is the transmit section, and green is the receive section. It's got to break things down, but we're just going to dig into the receiver a little bit. Now, as I mentioned, there's no mixers inside these parts. It's just directly connecting like an antenna or some RF filters, or maybe a down converter that you might have to the ADCs. After the ADCs, you'll have this programmable filter that you can use to do IQ correction if you want, or some low-pass filtering if you need to do that. It's completely programmable. You have a mux that will split any of those 4 ADCs into a set of coarse digital down converters. And these are essentially an NCO and a number of half bands that will decimate the signal for you. And then that can be fed into another mux that will provide another set of more finely tunable down converters. Okay, and if you kind of want to take this up a notch, you can put multiple of these down and build up a larger phase array system. So this is a quad MXFE board that gives you 16 channels at 4 gig a second, which is kind of an insane amount of data back and forth. And just for reference, that's what a Pluto is next to this guy. So it's kind of a beast of a system. But how do you deal with like a device like this with gigahertz of bandwidth? Do I just like connect it to GNU Radio and go? I wouldn't really recommend doing that unless you have some futuristic quantum computer or something that can kind of handle that data rate. Now, in practice, like even FPGAs have a hard time dealing with like the Nyquist modes of these parts because they can produce 4 channels at 2 gigabits a second. And the common strategies are you can use like vectorized blocks, like Xilinx has these super sample rate blocks, which are really useful, and even HDL Coder has vectorized blocks that are allow you to kind of deal with data rates at that speed. But typically, you don't use the part in Nyquist mode for complicated things. So Nyquist mode just means you're maxing out the rate of the chip. Typically, you can't run an FPGA that fast with a lot of combinational logic at that speed. So you'll have something like a energy detector, and then once you know that you have some interesting signal, you turn on all the digital down converters, and you look specifically at that channel that you're interested in. And that's why those channelizers exist, or that those digital down converters exist inside the system. Okay, so that was just a quick run through.
Thank you very much, Travis. Perfect, thank you.
I promise we won't have that problem here. This is all I have. This will be pretty quick. I just wanted to say hi. I'm Jacob. I'm with Sandia. We're a federally funded research and development center out of Albuquerque, and we use GNU Radio a lot. We're really happy to sponsor the conference this year, and we're hiring software radio expertise. We're also hiring hardware radio expertise, but that's not really this. We're talking on Thursday about some extensions to GNU Radio's PDU functionality for bursty signal processing. Might be interesting. Anyway, that's all I have. Thanks.
Thank you, Jacob.
All right, 1 bit ought to be enough for anyone. This is kind of inspired by Ben's opening yesterday. He showed this this photo of the circuit that I happened to put together for some work that Dominic Spill and I did. We did a series of talks called Ridiculous Radios, or in one case, Revolting Radios. And we were showing how people could improvise radio circuits out of all kinds of things. And in this case, we pulled a tuner out of an old VCR and connected it to GreatFed, our kind of general purpose microcontroller platform, to implement a software-defined radio. And if you look really closely in this mess of wires, there's 1 capacitor in there. So that's the extent of the circuitry, is that one 220 picofarad capacitor, and the rest is all just wiring. And so the way this works, if you look at the big box on the right, that's the tuner. So it's just an analog RF tuner that like has some amplification and filtering and a mixer. And it gives us an intermediate frequency on its out pin, number 18. And the intermediate frequency output is coupled over to a general purpose I/O pin on the GreatFed. And so we're using this general purpose I/O pin as a 1-bit analog to digital converter. 1-bit analog to digital converter. So if you're looking at our HackRF or any of the other fine SDR platforms that are being shown off in the room next door, you'll see all kinds of folks talking about how ours does 12-bit sampling or 14-bit sampling or whatever. You can do a lot with just 1 bit, it turns out. And we have a little trick there. One way I was able to reduce this down to just 1 capacitor was by using a DAC, digital to analog converter output on the GreatFed to provide a DC bias to get this thing right around the threshold voltage of that general purpose I/O input. And this worked astonishingly well. Like I expected it to work, but it worked actually a lot better than I expected. And so Dominic and I started talking about like, what else can we do? Well, one thing you might be wondering is, well, why in the world does this work at all? How can you pick a signal out of just 1-bit samples? Well, we use the trick of oversampling and decimating. Oversampling means we're sampling at a higher sample rate than you might expect that you need. But then we reduce that sample rate in software, and that's what decimation is. And so if you imagine that you have a bunch of samples in a row, and every single one is either a 0 or a 1, then imagine that you just averaged every 2 adjacent samples together. If you average these together, every pair of adjacent samples, now you have a sample stream that looks something like this. And we've reduced the sample rate by half, but notice that now there are intermediate values. Sometimes a sample is 0, sometimes it's 1, but sometimes it's 1/2, which means we actually need another bit to describe these samples. If we do this again, we average these together, and now we only have 4 samples here, but we have more intermediate values, which means we've needed more bits to describe every individual sample. In other words, as we reduce the sample rate, we get to trade that excess sample rate for dynamic range. So we gain dynamic range in software instead of having dynamic range provided to us by some fancy analog to digital converter in hardware. The averaging of 2 samples together is a good illustration, but in reality that's just a crude low-pass FIR filter, and we can do a much better filter, do the same trick, and however much we decimate by, however many times we have the sample rate, we gain another bit of dynamic range in software. And we were thinking about what else we could apply this to, and had this idea that maybe we should make an add-on board for our GRCon platform that allows us to sample the 2.4 gigahertz band. And the reason why we're interested in 2.4 gigahertz is because Dominic and I have been for years very focused on trying to do Bluetooth monitoring. And the holy grail of Bluetooth monitoring is sampling all 79 channels of Bluetooth simultaneously and demodulating them all and making a low-cost all-channel Bluetooth sniffer. Instead of spending tens of thousands of dollars on a piece of test equipment, you should be able to have something that costs less than a HackRF that does this. And this is my latest software-defined radio receiver design. It is a dual comparator, and that's it. The reason it doesn't have an RF section is because this is just a demo or a test prototype, and I just plugged it into a HackRF and piggybacked on its RF section. But the next revision, but even that was effective. And this is a spectrogram in which you can see some Wi-Fi activity on the right-hand side, and all the other little bursts are in fact Bluetooth packets that I was able to decode using this thing. And the next revision of Quince, which I should be assembling next week, actually has its own little RF section in addition to the comparator. And we should be able to do very low-cost all-channel Bluetooth sniffing. And the reason Bluetooth is such an attractive target for this 1-bit sampling trick is because the channels are only 1 megahertz wide, but the band is 80 megahertz wide. And so we already are going to have this high ratio of sample rate to the actual bandwidth of an individual transmission. So we get all that benefit of decimation kind of for free. Thank you very much.
All right, thanks, sir. So I got talked into doing this by Derek Kozel, pretty much 24 hours ago, because I was sharing with him kind of my experience as kind of a first-year GNU radio enthusiast. So my name's Hayden Nelson. I'm in marketing at National Instruments, and while I'm not new to kind of RF and DSP, I've worked around a number of defense research labs doing radar and electronic warfare, and National Instruments doing wireless communications work for a number of years. About a year and a half ago, I joined the software-defined radio team, and last year was my first trip here to GNU Radio Conference, and I left feeling pretty inspired, a lot of great talks, and just was amazed by the community, and found myself going, hey, I want to get more involved in this. And so, as a pretty technical person, I, took it upon myself to, work at NI. I grabbed a couple USRPs and started playing with some of these open source tools and was having a lot of fun. And so as a proper Texan, I am a well, actually, one other point before I go into this slide was I'm going to make fun of something here is a K5GNU. So I went out, I felt I better get my ham radio license or else no one in here will talk to me is kind of what I figured out was probably the case. And so I took my, not at the event, but I took my ham radio license as Derek had indicated, but without studying, passed it. Or I think you were saying that, Ben, so I encourage y'all to do that on Friday. And I was amazed that K5GNU was actually not taken as a technician level thing. So I grabbed it, and I feel kind of guilty a little bit about that, because it's like I'm relatively new to this community, and I got a really cool call sign. So I apologize. But most of y'all are extras. I'm still lowly technician. But I figure some of y'all may find that entertaining. And as a proper Texan, I do have a big truck, as you would expect. I think it's disallowed to drive anything other than a large truck in Texas. It's state law, I believe. And so this is a picture of my top of my Tacoma. It's not a big truck, but it's and I put a rack on there, and I found myself doing a lot of camping and off-roading, and I had a ham radio, and I had my USRP, was playing with GNU radio out in the campground, and had all my fellow campers kind of looking at me like I was, spying on them, or I was, something of this nature. But I found myself just having fun with it and getting involved with it. And this is actually a picture of my desk. I told my boss the other day, I said, I think I need another screen or a laptop and a USRP, because I think there's about 9 screens on there. And I just found myself getting involved and installing this software and kind of playing with these different radios for just kind of things in my personal time. And I even messaged one of our folks in our apps engineering team at 11 p.m. on a Saturday night, and I'm sitting there building GNU radio, and I'm like, wow, I got a really active social life, and I'm building this software, doing software builds on Saturday night, so I know that also impresses you. But it's been a lot of fun, and I kind of went through this process of, it's not my full-time job as an engineer. I work in kind of the marketing spot, but it started ran into a few problems here and there, getting things installed and set up and running examples, and was like, wow, I kind of went through this. And just yesterday, we had our new users GNU Radio session workshop over here in the Columbia room. And for some of y'all who went, you saw the problem we had. We had people just pouring out into the hallway, and I was like, wow, there's a huge interest here in people, just fundamental concept. Many of you are experts, and what I'm about to show you next is kind of probably not for you, but for kind of some of the people just getting started, I was like, well, I bought a Raspberry Pi, and I've been kind of playing with that, and I got 2 minutes. YouTube, there's a lot of good tutorials online for those things. Well, there's some of that around the GNU Radio world, and GNURadio.org has some great tutorials, and I'm certainly we're not looking to replace any of that. It's there's a phenomenally good getting started resources on edis.com. But myself and Nate Temple, who presented last year at GNU Radio Conference, we're kind of starting this little initiative. This is very early. Called it SDR Academy. I don't know if it's the best idea. We're not doing academic, stuff, but it's kind of a collection of videos we're going to start building out, where we'll, just helping people get set up using examples for kind of from the intro to intermediate, and we'll be adding content over time. This is live now. It's not linked on edis.com. It's a little bit of, Nate Temple and I's little rogue project on the Edis website, but we wanted to do something that leverage what I've been doing and give back something to the community to help people get started and just, have a different way to, go through the experience of using these tool chains. And so that's kind of the story of my first year with GNU Radio, and I appreciate your time. Nathan, you're up next.
All right, so this is on just a quick talk through learned spectrum sensing. This is kind of featuring one of DeepSig's products called OmniSig and the OmniSig SDK. So we take a machine learning approach to wireless communications problems. And so we just work from samples and then train neural networks to do some task and integrate that with a whole radio system. So all of the rest of modern communications is all based on optimization of some objective. So why not deep learning? So if you're a deep learning skeptic, then I challenge you that everything else is optimization anyway, so why not try gradient descent? So this is showing, last night I captured some local spectrum around here. This is a LTE uplink band. So we have this tool that lets you sort of draw boxes around bursts of energy, and you can right click and label them. So this is, you would effectively be building a data set, and it all works on SIGMF meta files and data files, so it's all using kind of the standard way of labeling data. So you can kind of zoom out here and see larger time extents, and there's various tools for, if you double click, then it stretches the span of the whole time domain. You can go into this control panel and just sort of edit signal descriptions on the right there. So there's some kind of interesting mirrored signal from something. And we're just labeling all those as LTE uplinks. These larger things are just called LTE, so that's the downlink. This is some CDMA 2000 thing. And then you can click this export button, and you're going to get out a saved version of that SIGMF meta file with these annotations in them. All right, so then you can come over to this training page, select the files that you want to train with. So right now we're just going to train with this truncated recording. It shows you what signals are in your data set now, and you can just sort of start training. And then you let gradient descent kind of take over. And there's a lot of complexity sort of hidden behind the scenes here that we're not going to go into here. And then once you start training, then there's this timer that starts, and you get a bunch of log messages that you're partially through some training epic, and then you get this loss plot where you see the training and validation loss. And if you wait long enough, then it starts decreasing here. There's this kind of interactive remote control tool you can use. You can use this to just print your losses out, then get a saved model, and then run that model in the runtime environment. And this is on true test data. So this is running on data that was not used for training. And you can see we're detecting all of the little bursts, and we have all of the downlink carriers. And it's all in one forward pass from samples from, in this case, it was a USERP B200. And the whole thing was trained fairly quickly. So if you're interested in that, please come talk to us at our booth. It's over there in the corner. And if you're interested in working in this area, then also come talk to us.